we have the expected value or mean. It's called E of x, right? That is the average weighted by probability. So that is the sum of four values v times the probability that you get that value. We have the variance of x, which is the average of weighted, of course, of distance to mean squared. So this average is how far away is every value to the mean. If you think about it, this is the values. Let me write it on this side. This is the values. Somewhere here is the mean. This is E of x. If I pick any value, that is the distance to the mean. So it's the average of those things squared. So if I'm to write a formula for it, this is expected value of x minus the mean squared, which is the same as sum over all the values of probability of getting that value times, instead of the v, which is the values, we put in here v minus E of x squared. So it's an expectation, but not of the values, not an average of values, but rather an average of those distances squared. So it's weighted by how often are you likely to see those distances. Not clear on the board?
No, it says weighted of distance what? On the, yeah, there.
Distance to mean.
Okay,
Distance to E of x.
thank you.
So if you look at any value, you say, okay, how far away is to the mean? You square it, and you want the average of those things. Now that average has to be weighted by the probabilities, because some of them are so unlikely to happen, those have low weights, and some of them are very likely to happen, they'll have big weights. The standard deviation, I'm going to write it in the same group here, is just the square root of variance. Or the variance is the standard deviation squared. And finally, the entropy is also an expected value. The average of value rarity. How rare things are. So this is an average of the values themselves. In a die roll, those values are what? In a die roll. What are the values I can get from a die roll? 1 to 6. This is an average of how far the values are from the mean squared. So in a die roll, what are those squares? What is the distance to the mean? Pick a value, say pick the value 5. What is the distance to the mean squared?
The 1.5 squared.
So if I get a 5 in a die roll, what is this value in here? Who's V? V is the 5 I got from the die roll. Who's the expected mean of the die roll? 3.5. So how much is this going to be? 5 minus 3.5 squared. What if I roll a 6? What if I roll a 6? Yes.
6 minus 3.5 squared.
Right. So for every value is that value minus the mean squared. That's what I'm averaging. So because I'm averaging, I take into account probabilities. In a fair die, all the probabilities are the same. so I get a straight arithmetic average. But if the die is not fair, I don't get a straight arithmetic average. Some values might be far more likely. In here, I'm averaging rarity. So what rarity is logarithm in base 2 of 1 minus the probability of that value, 1 over the probability of that value. We'll see why that formula makes sense theoretically. For now, you can just trust me, that's the one. So for every value, I look at its probability. This is using the value, this is using the distance to the mean squared, this is using this rarity. How rare is that value? And other than that, it's just a regular expectation value. So the expected of rarity of x, which is the sum for all values of probability of seeing that value times the logarithm base 2 of 1 over the probability. So like any expectation formula, it's weighting some quantity, it's averaging, it's an arithmetic average, but weighted by probabilities. All three are expectations. This is the average of the values, the straight mean, average, weighted probabilities. This is the average of distance squared, weighted by the same probabilities of that likelihood to happen. And this is the average rarity, which is an expected formula, same probabilities, times this rarity notion here, log base 2 of 1 over the probability. The only observation I want to make here, this works for non-numerical random variable. So what I said here is numerical, I need it to be numerical to compute this, right? If those values are not numbers, I can't take an average. If suppose the values are colors, or forms, or cities, or cars, or people, can I take an average here? No. How about here? This d minus e squared, just e of x alone. To get e of x an average, I need to be able to average things, and I cannot average things that are not numerical. I cannot average colors or people. I mean, I can define for colors some numerical association, say red is some big representation in values, like computers use numbers for colors. Sure, as long as I use numbers, I can do averages, but generally speaking, I cannot just take any random variable and average it unless it's numerical. For here, I can do this for any random variable, right? Because the p, the probability of getting a value is whatever the probability is, and this is the same p. So as long as I know the probabilities of color or people or shapes or books or whatever, I can apply this formula just as well. This formula works for any random variable. This measures average, informal notion. This is an average. This measures variability. And this measures randomness. How random. So there's a difference between a die being variable and being random. We'll see that in a second. It's a very related notions, but they're not the same. A die can be very variable, but not so random. And it could be very random, but not so variable. Okay? So before I move on to some examples here, what I want to do is to explain in practice the difference between, that's a theory, right? It's all very good. What do we need to do that? We need to know all these V's and all those P's, right? That's how you apply this formula. All the problems we done, say compute the average of a die. How did you do it? Well, you knew the probabilities of a die, and you knew the values, right? And here's the same. How do you compute the variance of a die? Well, you plug in the values 1 to 6, and you know the probabilities. What if I say I have a die, I don't know its probabilities? Maybe it's fair, maybe it's fatal. How can I compute variance and expected values? If I tell you, hey, here's a die, I know the face is 1 to 6, but I don't know the probabilities. Maybe it's fake. How do I get its average? What do I have to do to get that average? Or to estimate the average, approximate the average? What would you do if I say I have this die? I don't know if it's fake or not. How can I find out its probabilities? Yes?
You would just start rolling it and keeping track of what you get.
Right. It's what I did last, you remember what I did last time in class? I didn't roll it with my hand, I roll it with MATLAB, with my computer. MATLAB is great at rolling die, by the way. And that code is online, you should download and run it. Installing MATLAB is a piece of cake. Northeastern has a license for it. Very useful language for math and computer science and engineering. So I would definitely install MATLAB, download that code, and start rolling dice and flipping coins and all that, just to see how it works. That was that experiment, right? We rolled the die, and what happened when we rolled the die? Let's say uniform die right here. Rolls. Remember there was a sort of a picture? That was a histogram, there was what? Values, right? The values of a die are 1, 2, 3, 4, 5, and 6. And we keep track, like he says, of the count. So we got these bars of how many 1s and 2s and 3s you've seen, right? If you pay attention to that histogram that was on the display, you notice that those bars are not perfectly identical. So when you roll a die, even if you roll it 10,000 times, and if you have a perfectly fair die, it's not guaranteed to get exactly the same counts, but you should get approximately the same counts. Right? As opposed to say, here's I have a die that has the same values, 1, 2, 3, 4, 5, and 6. And we had big 6s and big 1s, remember? Those are big. And then these are much smaller, those columns. These are counts, right? Again, this was not a fair die, has much more probability in 1 and 6s. When we roll it, we're going to see bigger columns for number of 1s and 6 observed, less for 2, 3, 4, and 5. Right? But my point is, empirically speaking, so I'm going to create here a table that I'm going to extend this to say what happens empirically. Empirically, I have a sample. A sample is I roll the die 1,000 times, or I toss a coin 10,000 times in the air, or I sample cars from a parking lot, right? Or I sample meet and grades. That means I don't know the exact probability of getting a 70 or 80 in the midterm, but what I can do, I sample a lot of students and then I estimate those probabilities empirically. So if I have a sample, we call these observations. I don't have these probabilities. I have values, like with the die roll, I have 1, 2, 3, 4, 5, 6, and I have the counts. I know how many times the die rolled 1s and 2s and 3s and 4 and 5 and 6. How can I estimate this mean? If I have these observations, I don't have probabilities, but I did roll the die 1,000,000 times, and I got the counts. I know how many 1s, how many 2s, how many 3s, how many 4s, how many 5s, and how many 6s I've got. How can I estimate? Let's not put equal, let's put estimate. This is empirical mean, which is an approximation of that. That's the exact mean if I knew the exact probabilities. Now for this die I have again, I don't know if it's fake or real. I don't know if it has been changed. I don't know if the manufacturing process somehow was a little bit off, so the die is not perfectly 1, 6, 1, 6, 1, 6, 1, 6 likely probabilities. So how can I roll it 1,000,000 times, and then what do I do to estimate its average?
You can sum up all of the samples.
I sum up the values, right? Sum of the values. The rolls that I've seen, and all the 1s, 2s, 3s, everything I've seen, I sum it up, and then
And then divide by the number.
divide by the number of values. This is called an estimator. It estimates that, and it estimates it for any die. whether the die is uniform or not, when I roll it 1,000,000 times and I sum up these values and take the average, I get an estimated of the theoretical average. This is theory. This is empirical. There is a difference between knowing theoretically all the probabilities and computing the theoretical average, or rolling the die 1,000,000 times and compute its empirical average. If you roll it enough times, you should get the same. This becomes a very good estimator for the mean, but you have to roll it a lot of times. And there's a lot of statistics who tells you how many times you need to roll it to have a certain confidence. If you want to be 99.9% confident that your average is very, very close to the real average, the theoretical average, you need to roll it 10,000,000 times to make sure that the average cannot be off. How about the 76 in the midterms? We say the average of the midterm is 76. Which average is that? Is it the theoretical or the empirical? Hmm? Yes.
Empirical,
Why?
because you took all of the actual exam results and divided by the students taking it.
Instead of rolling a die, I give to 580 students the midterm, right? And that's actually a sample. I got a bunch of people taking the midterm and I average, that's how I got the average, right? Do I know the exact probabilities for this midterm to get, say, what's the probability to get a score of 82? That's a possible value in the midterm, 82. So what's the probability of getting an 82 on it? I'm not sure. We're talking about all the CS majors in the world, right? That ever lived. This is a universal notion that you need to have this property. What is the probability to get an 82 in this midterm? I'm not sure. I can estimate it by taking a sample. Say, oh, here's the midterm. How many people got 82? Well, 25 people out of 580. So then I can estimate that probably 25 people out of 580 got this grade. But that's a sample. If I give this midterm next year, or the year after, I may get a slightly different estimate of the average, right? Everything that's done with true data, with observations based on a sample, whether it's the midterm in a class, or whether it's the die rolls, or whether it's playing cards, it's an empirical average. To compute a theoretical average, you need to know the exact probabilities. So if a problem says I have a fair die, I can tell you the probabilities are exactly 16, 16, 16, 16, 16, compute average. It refers to this. Because it gives you the probabilities, ask you what is the theoretical average. If the problem says, I have 600 students that took the midterm and I observed the following grades, compute the variance. They mean this. They mean you have a sample, how do you compute? By the way, how do I compute the variance for a sample? I don't have the probabilities again, but I took the midterm, 600 people to the midterm. How do I estimate the variance? What do I do? Yes.
You sum up v minus e of x squared and then divide by the number of values.
V minus,
E of x squared.
but it's dc of x. Let's put a hat to it, right? I don't have the theoretical e of x, so I have to estimate the mean first, 76. I'm saying that's close to the mean. I'm not sure it's exactly the mean, it's the empirical mean. And then I sum up those things squared, right? For each value that I observe there, all the grades, and I divide by the number of values. I should say observations here. Value of each observation, number of observations. I'm going to make that a little bit more clear. You guys have to be in data problems, in real problems. What is the difference between a value and an observation? What is an observation in the case of midterms? How many observations did we have with the midterm? How many? Almost 600. So what's an observation?
Grade.
One student is an observation, right? Every student is another person taking the midterm, is another sample. So the sample contains observations. Sample is a set of observations. What is a value? The actual score. What are the possible values for the midterm? 0 to 100, right? So there's 100 possible values. What are the number of observations that are possible? They're all the students, right? If I have 3,000 students next year, I'll have 3,000 observations. But still only values from 0 to 100. So you gotta make a difference when you see data. What is a value versus what's an observation? An observation is a data point, is a student. The value associated with that observation is the grade in the midterm. The grades are still from 0 to 100 for everybody. So when you take a student, even if you have 5,000 students, the observation is the student. The value is a number between 0 and 100 is the grade in the midterm. How many people follow me here? All right. So it's not hard to prove that this is getting very close to the theoretical variance if you take enough observations, right? For this, we won't address this today, how to do it, but you have to effectively estimate probabilities. P of V, let's put a bar to it, that's empirical, is the number of occurrences divided by the number of observations. So effectively, if I want to know for a die, what is the probability to see a 1? How do I estimate that? I roll the die 1,000,000 times, I count how many ones I've seen, and then I say, is the occurrences of 1, occurrences of that value, divided by how many times I roll the die. And then I still apply the same formula. Apply formula. For now, those P's of V's are, let's put bars. Bars means are not the real theoretical ones, are the ones estimated from data. So I know that's not the purpose of this class now, but a lot of the data stuff that you're going to do in computer science, when it comes to apply all this stuff to real problems, you got to make a clear difference between a theoretical variance or entropy or mean, which only exists theoretically, because in practice you're never going to have exact probabilities unless the theoretical problems specify probabilities. But in practice in data, whether you have medical patients or whether you have bank records or whether you have real cars, you're never going to know the exact theoretical probability of a car to cost so much money. In practice, you only have samples. You have a lot of cars, a lot of patients, a lot of students, a lot of houses. You can estimate the average mean of a house, but you cannot know for sure what is the probability for a house to cost so much money, in theory. So in practice, when you apply in practical realm, you're going to get on this side. So now, I want to take some example here. I have those 3 dice that I start drawing. So I have another die here that is die biased 3 and 4. This is biased 1 and 6. So it's big 1 and 6, but not so much in the middle. This is uniform, so this is 1, 6, 1, 6, 1, 6. And this is, say, what is it here? I think it's 310, 110, 110, 110, 110, 310. And this one that I have here, 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. This die is big on 3 and 4s and small. This is 110, 110, 310, 310, 110. Now these are theoretical dice. Those are not, if I roll a die in practice, I get counts, I get those bars. I put them here to remind you of a notion of histogram. When you roll a die many times and you keep track of its counts and you plot something like this, how many 1s, 2s, 3s I've seen, that's called a histogram. You can do the same for the meters. Those are the histogram that my MATLAB code was plotting. It keeps track of those counts and shows you some sort of shape, how the stuff looks. Now, my dice here are theoretical, meaning I know the exact probabilities. So when I know exact theoretical probabilities, I'm here, right? I can compute the theoretical mean, variance, and entropy. So that's what I want to do. I want to compute the mean. Let's start with this uniform die. What is the average? So x is the value of the die. Random variable value of the die. We already did this, right? This is sum over k equal v, let's say v. V equal 1, 2, 6 of v times probability of v. Short notation. We already done this. This is 1 over 6 times 1 plus 2 plus 6. How much is that? The average of the fair die. 3.5. How about in here? The same, theoretical average. Again, I can do theory because I know the exact probabilities. I don't have to take a sample. I don't have to roll this die, not even once, because I know the probabilities. So I'm not going to roll these dice. I'm just going to compute the theoretical values. I want to emphasize this. I know I'm repeating it for the 4th time. There's a difference between a die that's theoretical and we know its probabilities. We don't have to roll it. We just know what's going to happen. And a die that we don't know what probabilities it has. So to do anything, we have to roll the die to find out how many 1s, 2s, and 3s, and 4s we have. Same thing for the midterm. If I want an average, I have to give you the midterm and get back the grades to compute an average, unless I have probabilities exactly for each grade. Right? So for this die here, what is the expected value? Is the same, sum of the values v times p of v, although now probabilities are not uniform. So I'm going to break it into who has 1 over 10 probability. It's 1 plus 2 plus, who has 1/10 probability? 5 and 6, right? Plus who has 3/10 probability? 3 and 4. Now how much is this? Let's say 1/10, we divide by with a 10 at the end. How much is 1 plus 2 plus 5 plus 6? 14. 14. How much is 3 plus 4 times 3? 3 plus 4 is?
7.
7 times 3?
21.
Plus 14? 35. By 10, that's 3.5. Are you guys surprised to see that this die has an average of 3.5? Why not? Why is it still 3.5, although it's not uniform?
Still symmetric?
It's symmetric. Whatever is big on this side of 3.5, that's the mean, right? It's exactly the same on the other side. It's not a uniform die, but it's still symmetric to the mean. This side of the die, the lower side, it's symmetric to the other side, which means the mean is still at 3.5. For everything that got a little higher in here, the 3, also the 4 got a little higher, so 3 compensates with 4, and then 1 with 6, and 2 with 5, same mean. How about here? Is this symmetric? Symmetric, right? So what's the expected value of this die? 1/10 goes to who? 2 plus 3 plus 4 plus 5, and 3/10 goes to who? So in here, how much is 2 plus 3 plus 4 plus 5? 14. 1 plus 6 is?
7.
Times 3? 21 plus 14?
30.
35 by 10? Still 3.5. How about the variance? It's going to be a little intensive. Okay? Let's see. What's the variance here? Which variance am I computing? The empirical variance based on a sample on die rolls, or the theoretical variance based on the exact probabilities? Which one am I doing here? The theoretical, because I don't have die rolls. I have theoretical dice. Somebody gave me the probabilities for them. I'm not rolling those dice at all. I'm in here. If I give you a die roll that you don't have probabilities and you start rolling it, then you're here. So I'm in the right side. What's the variance? Is sum over all the values, right? of, what did we say? It's not V, it's V minus the mean, that's 3.5 squared. So 3.5, I already have the mean, so I put the mean there, times the probability of V, right? So how much is this? This is easy because it's 1/6 for everybody. The probability of every single value is 1/6. And now I have to do what? What is the sum of squares? Is 1 minus 3.5 squared plus 2 minus 3.5 squared plus 3 minus 3.5 squared plus 4 minus 3.5 squared plus 5 minus 3.5 squared plus 6 minus 3.5 squared. I have to take all each values, subtract the mean, and square it. So now how much I get in there? 1/6 times what? How much is 1 minus 3.5 squared? 2.5 squared, right? How much is 2.5 squared? Hmm? 2.5 squared. Let's say 2.5 squared for now. And there's two of them, right? 1 minus 3.5 and 6 minus 3.5, they produce the same value. Both of them are 2, so that's two of them. Plus, how much is this? 2 minus 3.5? 1.5, right? 1.5 squared. It's also two of those because this is 1.5. Who else is 1.5? 5 minus 3.5, it's also 1.5, right? Are you guys following me? Hands up. Okay. There's two of those, and then there's two of what? 4 minus 3.5 and 3 minus 3.5, both of them are 0.5 squared times 2. So that's a calculation. 2.5, 25 squared is how much?
6.
So that is 1/6. I'm going to take this 2, 2, 2, 2, and I'm going to put it 2 over 6 here. And then that is 6.25. That is 2.5 squared. How about 1.5 squared? 15 squared is what? So this 1.5 squared will be 2.25. And 0.5 squared is 25. So 0.5 squared will be 0.25. So this calculation, if I done it correctly on my piece of paper here, will be 2.91. Just a matter of adding up those numbers, multiply 2 by 6, 2.91. That is the theoretical average of a fair die. How about in here? What do we do here? What's the variance in here? Well, we apply the same formula. Sum of the whole values, V minus 3.5. Same average, so 3.5 is the same. Times the probability of that value. Although now I can't say everybody has a 1/6 probability, because that's not true anymore. There's difference. So there's two categories. There's the die rolls that have 1/10 probability. So what are those? 1, 2, 5, and 6. So that is 1 minus 3.5 squared plus 2 minus 3.5 squared plus 5 minus 3.5 squared plus 6 minus 3.5 squared, right? Those are the ones with 110, 110, 110, 110. And then I've got the other two, which are the 3/10 values. Which ones are those? 3 minus 3.5 squared plus 4 minus 3.5 squared. So what is that? These are who? Who is this? 1 minus 3.5. We already computed that in there. 1 minus 3.5 is 2.5, and if we square it is 6.25. So that's 6.25, and there's two of them, right? Because it's this and this, they have the same value. And 2 minus 3.5, that is 1.5 squared. How much is that? 2.25. There's two of them, right? Because there's this is 1.5 squared and this 1.5 squared. Plus 310 on this is 3 minus 3.5, that's a 0.5 squared. How much was that? 0.25, and it's two of them. Yes?
So on the one on the right, the uniform die, if the variance is the like average distance to the
Square.
mean- Oh, it's average distance squared.
Right. So it's take the distance to the mean, square it, and then average those weighted by probabilities.
So then if you square root that,
You get standard deviation.
just
You get the average distance to the mean, but in a square sense of average, not in the absolute distance of average. So if you take the absolute distance is a geometrical difference, which is the absolute values, and you average those, you don't get standard deviation. You have to square them, average the squares, and then take the square root. The square root of 291 will be the standard deviation of a fair die. Okay, back in here, what do we have? How much is this? 6.25 plus 2.25 is 850 times 2,
17.
17. 3 times, how much is this? This is 0.5 times 3, how much is that? 1.5. I put the 10 outside of common factor. So if my calculation is correct here, I'm getting, for these dice, 1.85. You can see that's correct, it's 18.5 divided by 10. Standard deviation will be the square root of 1.85. How about on this die here? Those very similar, except the high values, high probability values, are not 3, 4, are 1, 6, yes.
Conceptually though, why are we squaring? If we just want to find the average distance from the mean, why don't we do the absolute average?
Right, that's not working with math. That absolute, while makes sense, like common sense, exactly what you say, if you do the math of it, when you start taking differentials, it's not a nice way to, you can do that. You take the average to the mean and you can call it that. It's a statistic. It's actually a statistics, average to the mean in terms of absolute value. Has two problems. Math is not easy because the absolute value is not differentiable, while the square is. The other thing is, variance typically, it's, you want to be more sensitive to high values. I explained this a little bit at recitations yesterday and Wednesday. The squares are more sensitive to high values. The absolute distance to the mean, it's uniform on all values, it's a straight average. So if distance is 10 times more than another distance, it contributes 10 times more to the average. But in a square average, if a distance is 10 times more than this other distance, it contributes 100 times more to the average because it's squared. So let me say that again. If she is one unit away from the meter median, so she's got a 77, and he is 10 points away from the median, so she's got a 66 out of, away from 76. If I do the average distance of 10 and 1, what he was asking about, what's the average distance between 10 and 1? 10 plus 1 divided by 2, right? And that will be his distance contributes 10 times more than her distance. But if I square it, like in the variance, what is now his distance squared? 100. What is her distance squared? 1. Now, to that variance, he contributes 100 times more than her distance. So the variance is far more sensitive to outliers, to things that are far away from the mean.
Why do we want that though?
There are statistics that's the average distance to the mean, and you can use that if you'd like. In most problems, people want to be more sensitive to high distances, to outliers. Also, the math, it's a lot easier. So you can take it as a definition, and if you like to use the other one for some problem, you can. There's also averages that are the other way. They are sensitive to small values. depending on the problem you want to solve. Let's compute this variance here. So I get the 110 of what are the squares of 110? Is 2 minus 3.5 squared plus 3 minus 3.5 squared plus 4 minus 3.5 squared plus 5 minus 3.5 squared. Those are the guys who have the 110 probability. And the 310 applies to who? 1 minus 3.5 squared, 6 minus 3.5 squared, right? So I get 110. What do I have here? 2 minus 3.5, that is 1.5 squared is, how much should we say? 2.25 times 2, there's 2 of them, right? It's this guy and this guy, right? And then the other distance is 0.5 squared, that was 0.25, there's 2 of them. Plus 310, how much is this here? 2.5 squared was 625, and there's 2 of them, so it's times 2, right? So now this would be like before 110, how much is 2.25 plus 0.25 is 2.5, multiplied by 2 is 5. And then the other guy is 6.25 times 2, 12.5 times 3,
37.5.
very good. So 37.5 plus 5, that's 42.5. If I divide by 10, how much is that? So that is the theoretical variance. Again, I can conclude this because I have all the probabilities, right? Those 3 dice have the same average because they're all symmetric. Do they have the same variance? 4.25, 2.91, 1.85. Very different variances. Why is this variance of this die so big in English, in common sense terms? Why this guy has a large variance?
Because the majority of the values is far away from the mean.
Exactly. The majority of the value, the 1 and 6s, are far away from the mean. Why is this die has such a small variance? Somebody else? Yes.
The majority of the values are close to the mean.
Exactly. And this is in between because it's not, on average, the values are not that close to the mean, like this guy, but they're not as far away as this other die. It's, more spread, so it's not a lot close to the mean, but it's not as spread as this die, so it's somewhere in between. Again, variance measures, on average, how far away values are from the mean, squared. We already said that. It's not absolute distance, it's squared. And you can see why, say this is a fair die variance. This die moved a lot of values closer to the mean, so its variance dropped. This die moved a lot of values far away from the mean, so its variance increased. Although they have the same exact mean, all 3 dies. Right? So when you talk about distributions like those histograms, how many 1s and 2s and 3s you've seen, you want to take the mean, like we say, the mean of the midterm was 76. But you want to say more about that distribution than just 76. Because if you just say the mean, it could be like this, it could be like that, or like that. You want to characterize the distribution. It was 76, but if it's flat, that means, well, in this case, having a 80 or 90 is equally likely to having a 0. That was not the case for the midterms. The distribution of the midterms was not a flat distribution. Nor it was this distribution. It was not the case that so many people score 100 and so many people score 0 and nothing in between. Nor it was this case, but this is closer to how the midterm distribution looked like. The high values were not around they were around the mean 76, but a little biased to the right side. So if you want how the distribution of the midterm looked like, this is 76, it was like that. So when you characterize a distribution, you have to give more statistics than the mean, Because the mean alone doesn't tell you which kind of distribution you have.
For things like being one standard deviation away from the median, being two standard deviations away from the median,
Right.
Like that's like associated with like a
So if you know what distribution you have, say it's a normal distribution, then you know exactly one standard deviation. If a normal distribution, you guys know how it looks like? It's the one that have this shape, right? The mean, of course, is right here. The standard deviation, you know exactly how much chunk of the data is going to eat the standard deviation. One standard deviation away is that. Two standard deviation away is that, right? So that's the mean right here. This is one standard deviation, two standard deviations. So I think in a normal distribution, if I remember correctly, about 68% of the data it's inside two standard deviations, and three standard deviations, about 95% of the data. But to do that kind of estimation, you need to know the shape of the distribution. If I have a very weird distribution, well, it looks like that, I can't make, say, within standard deviation away from the mean, I have so much data, because within one standard deviation of the way, I have no data at all in here. So if you know the shape of the distribution, you could say things like, if I move away, how many people are from 76, one standard deviation away? We say standard deviation is 14. Remember, for the midterm, I tell you, empirical standard deviation was 14. So what is one standard deviation away from 76? On this side is 62, because it's 14. On this side is 88. If the distribution would be normal or Gaussian, but it's not. But if it would be, I could say between 62 and 88, you should see roughly 45% of the grades. Because I know in a normal distribution, 45% of the data is within plus minus one standard deviation. But your grades distribution is not normal. So I couldn't just say that, right? Because I need a normal distribution to make that kind. In MATLAB, you can, for many, many distributions, MATLAB will tell you within one standard deviation how much data you have for like 25 distributions, including the normal. Again, your distribution of the grades was not normal, so you, even only if you approximate with the normal, you could say such things. How about entropy? What's the entropy here? Has a name. It's called H. So entropy has nothing to do with the values. Values don't matter for entropy. Only the probabilities matter, right? So what's the entropy of that? The theoretical entropy, the ones that I have the probabilities for. Because that's what we have here. We have theoretical dice. We don't roll anything. It's the sum of the values, right? P of the value times 1 over log base 2 of the value. Of course, everybody in this die has the probability 1/6. So 1/6 goes in front of the sum because it's 1/6 for everybody. How much can anybody compute for me? Sorry, it's log of 1 over probability. Log base 2 over probability. Now, this sum here is of log base 2. How much is 1 over probability?
Wait, that's for that one, isn't it? No, the 1/6, the probability of 1/6.
You're right. Okay, let's do this one first. Sorry, didn't wake up yet. Entropy is the sum for all values of probability of seeing that value, like for all expectations, times the log of 1 over that probability. So this is 1/6 because everybody has 1/6 probability in here, times the sum of what is the log, what is 1 over 1/6? 6 is log space 2 of 6. Can anybody compute that for me? Now, because this is constant, how many times I'm summing it here? This is from v equal 1 to 6. I'm summing that 6 times, and then I divide by 6. What is that going to be? That's going to be exactly this log, right? Log space 2 of 6. We're summing up 6 times of 6 oranges, and then divide by 6, you get 1 orange. How much is log base 2 of 6? Somebody with a calculator. 2.58. 2.58. How about in here? in here, not everybody, so the formula is the same, but not everybody has the same probability. So I need to break this sum into two parts. Is the part, the ones that have 110, right? What's up with those? Would be a sum of what? Log 2 of 1 over p. How much is 1 over p? If the probability is 1 over 10, how much is 1 over the probability? 10. And how many items I have in here? There's like 4 values, right? Values 2, 3, 4, and 5. But the values, again, for this entropy formula, the values themselves don't matter. It's only the probability of the value that matters. So the 2, 3, 4, and 5 don't appear in this formula, only their probability. And then I have the guys with 3, 10. It's a sum for values 1 and 6 of log of what? Log base 2 of? If the probability is 3 over 10, how much is 1 over the probability? 10 over 3. So, can anybody tell me how much is log base 2 of 10? 3.32, and I have 4 of those, right? I have 4 of these items. And 3 by 10 times 2 items, there's 2 values here, times how much is log base 2 of 10 by 3? By the way, you guys know a formula that I can apply here on this log? Log of 10 by 3 is what? Log of 10 minus log of 3, right? Everybody knows that formula? Logarithm base 2 of a by b is logarithm base 2 of a minus logarithm base 2 of b. That can make some calculations easier, but if he has a calculator, maybe he can do directly log base 2 of 10 by 3. 1.74?
Yeah.
Okay. So if we sum all this up, I have a formula here. I'm not sure if I did it correct last night. You guys can check that. I'm getting 2.36. Question mark, question mark, question mark. Because we don't know if that's correct. Just do that addition and see what happens. But that's how we compute the entropy. Again, big observation, if you have a red pen, write it in red, circle it, and put an exclamation mark to it. Okay? If you have a red pen. Entropy does not depend on the actual values, only on their probabilities. You see, there's no value here. I'm counting by the value, but the value itself does not appear in the entropy. So what do you think will happen for this die when I compute the entropy? For the purpose of entropy, what's the difference between this die and this die? There's no difference. They have the same probability distribution, just on different values. But values themselves don't count for entropy. So there'll be exactly the same calculation, right? It would be 110 times 4 times log base 2, 4 because there's 4 values of 10, plus 310 times 2 times log base 2 of 10 by 3. Assuming that calculation is correct, we get a 2.36. Those dice have the same distribution, just on different values, so they get the same randomness. Randomness does not depend on the actual value. Okay? So this is the kind of calculation that one might have to do. It won't be so bad, because it took me, what, an hour here. But you can expect problems like compute a theoretical, if somebody says variance or theoretical variance, they mean that. They have to give you the probabilities, or the mean, or the entropy. If they don't give you probabilities, they have to give you some sort of sample, saying, I did a midterm, I have 500 grades, this is my observations, how are they distributed? So, and then you have to compute this stuff. So now, I want to talk more about entropy. Why is that rarity? So why rarity is log base 2 of 1 over the probability. Rarity of a value. Why is that? People have looked at like how to encode things for transmission purposes. Let's see here where that thing is. So why this makes sense is because that is the optimal number of bits to encode. As in transmit. Value bit. Encode here doesn't have the meaning of encrypt. The purpose here is not the security to how to hide the value so you cannot find it. That was the RSA part, right? Where we encrypt something that if you see the cipher, you don't know what the message was. In here, the purpose is for communication. Communication bandwidth. So optimal, I mean the one that requires less bits to send a message over a wire. So here's what I mean. I have the following messages or symbols. A, B, C, D, E, F, G, H. If I use a fixed code, how many, I have 8 things, right? So you remember module 1, how many bits I need to represent 8 things? 3 bits, right? So let's assign some code of 3 bits. 0, 0, 0, 0, 0, 1. This is a fixed code, 3 bits. 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And then if I send a message, so in a fixed code, a message of length n, say n equal 100. Length is the number of symbols. If I send a message of 100 symbols, how many bits I have to send over the wire? If every symbol has 3 bits?
300.
300. So that implies you have to send n times 3 bits over the wire. Easy. If I have a message of length n, I can compute even a bits per character, like bits per character or symbol. It's of course 3n divided by n is 3, because every bit has exactly 3, right? How many people follow me? Okay, not enough. So what do I have here? I have a bunch of symbols and I'm creating messages, like I'm writing text. And every symbol would take 3 bits to send to the other side, by cell phone or by email or whatever. Takes 3 bits. How many bits do I need to send a message of 100 symbols? 300 bits, because every symbol would take 3 bits. And on average per bit, per symbol, if I have 300 bits over 100 symbols, that'll be 3 bits, of course, because every character has 3 bits. Again, who's up? Who's with me here? Good. Now, the interesting part comes in. These characters are not equally likely. Imagine English text. Are all letters equally likely to appear in text? No. Imagine names. Imagine cars. Is a Honda or Toyota equally likely with a Rolls Royce on the street? Not where we live, right? Right. Imagine grades. Are all the grades equally likely? No. Imagine anything you like and they're not equally likely, right? That's the nature of nature, is not uniform. So here are some probabilities that I cooked up in here. This is 1/4. B is 1/4. 1/8. 1/8. 1/16. 1/16. 1/16. 1/16. What does that mean is that this is not a uniform alphabet. When people write text, how likely is to see an A in text in this alphabet here?
Very
1/4, right? Which means every 4 characters on average, you see an A. How likely is to see an E in this alphabet? This is not English language, because in English, E is the most likely letter, by the way. E is the most frequent letter in English, so that's clearly not the English alphabet. Doesn't matter, that's a genes or whatever. How much likely is to see E in this text? 1/16. On average, every 16 characters you see an E. So it's a rare thing. So the communication people, whether it's cell phones or FaceTime or email transmission or routing, have been concerned for a long time. Wait a minute, why use 3 bits for every character if some characters are so much more likely and some other characters are not so likely? How can I send less bits on average for the whole text? I have to encode the whole chapter or whole email, but in that email or book, I'll have a lot of A's and B's, because I know the probability. So I'm in a theoretical world when I know probabilities. And I don't have that many G and H and F's. How can I change this code, the number of bits per character, per symbol, so that on average I send less bits? What do I have to do? If not everyone has 3 bits, some will have more bits and some will have less bits. Which one should have less bits and which one should have more bits, such that on average I send overall less bits for the same message?
The ones that show up more often should have less bits.
Right. If the ones that show up more often have less bits, on average when I send messages with a lot of A's and B's in them, I'm going to send less bits. So that's what this comes into play. This tells me what's the optimal number of bits per symbol. So if I am to use this code here, which is a prefix code, how we call this? There's many names. So variable length code. The entropy, this formula here, will tell me how many bits do I need. So this is using the number of bits is log base 2 of 1 over the probability. This is simply saying I need 3 bits because I need to encode 8 symbols. How many bits do I need? I'm treating all the symbols the same. How about in here? If I have this variable code, if A is 1/4, what's log base 2 of 1/4? Of 1 over 1/4. So 1 over 1/4 is 4. Log base 2 is 2. How about 4? How about the B?
2.
How about this guy?
3. 4.
If that's what I want, I'm not sure there is a code that does this. Right? Because you could say that's what you want, 2, 2, 3, 3, 4, 4, fine. But is there a code with bits that achieves this? But let's say it is. What's the average length for the variable code? For the same message. Same message, which is of length n. How do I compute that average? In here, I know it's not an average, it's exactly n times 3. Because every symbol has 3 bits. If you send n symbols, you're gonna send n by 3 bits, guaranteed. In here, I'm saying, I don't know how many A's and B's and C's are in there. But I can estimate, right, on average. Because I have the probabilities. So in n characters, in n symbols, how many A's do I expect to have? Right. So that would be a sum for every possible symbol. Let's call it S. the probability of that symbol times, it's n in front, let's say times n, right? This is the expected how many A's I have. Remember the tossing the coin problem? If the heads have probability of appearing 70%, and I toss the coin 100 times, how many expected heads do I have? 0.70 times 100, right? How many people remember from last time expected number of heads in a toss coin? Same thing in here. If A appears with that probability, and I have n symbols, right? My message is 100 characters long, right? It's from 1, 2, 3 up to n. Could be B, A, C, A again, so on and so forth. That's my message that I'm sending. The average means expected value, right? I'm not, for different messages, I get different number of bits, but on average, how many A's, B's, and C's I'm gonna see there, it's n times the probability of occurring. But for each one of them, I also have to put the code length, right? Because this is how many S's in message, and this is number of bits for each S, right? For A, so how does it look like for my example here? For A, what do I have? N is in front of the sum. For A, I get 1/4 times how many? What's the code length for A? If I realize this code length here. 2. I use 2 bits for A. How about for B? It's 1/4 times 2. C, D, E, F, G, H. For C is what? The probability of seeing a C is 1/8, and how many bits do I get to use every time I put a C in my message? 3. The probability for D is 1/8 times 3 bits for D. How about E? 1/16 times 4. 1/16 times 4. 1/16 times 4. 1/16 times 4. Plus. So n is in front of the sum, and it doesn't matter because I'm going to average anyway by n. So longer messages will take more bits. That's okay. I understand that. My concern is this now better than sending 3 bits per character? Gotta be better, because the values that occur a lot are only used 2 bits. These guys are the same. The 3 bits are the same here or here, so for every occurrence of them I get the same. These ones have more bits, but they don't occur that often. So it's not often that I have to send 4 bits. It's often that I send only 2 bits. So this ends up being, on average, is 2. If you compute this value here, 2 times n, of course. Is that right?
2 and 3/4.
Yeah, I got 2 and 3/4.
How much?
2 and 3/4. Yeah. And still that.
2 and 3/4, 2.75?
Yeah.
Okay, whoever wrote these notes. Anyway, get my point, it's smaller. So, 2 things in here. What value did we use to realize the code? To get, how do we get this 2, 2, 3, 3, 4, 4, 4, 4? That's exactly the rarity value, right? That's exactly log 2 of the probability. I can know in advance, if I know the properties, I know how many bits I'm going to need for this. I know it's 1/16. So I know the optimal way is to send log of 1/probability. That's 4 bits. And by the way, this whole formula here, what is the sum of probability times rarity? This is a sum of probability of each value times the rarity of each value. right? Because the 2, 2, 3, 3 are the rarity values, and the 1/4, 1/4, 1/8 are the probability values. What is this? Hmm?
Is it the entropy?
Yes. This is exactly entropy of the symbol. And there's a theorem, which we're not going to do, that says you cannot encode better than the entropy. That, of course, entropy times how many symbols you have. The more n there is, the more bits you're going to use. But on average, this BPC, the average per character, is the entropy. And that is optimal. Meaning, it's a mathematical theorem that says you cannot have a rate of bits per character, per symbol, less than the entropy. That is mathematically impossible. In that sense, that code is optimal. Because if we can realize this code, we get the best possible rate per symbol. In practice, that's how communication is encoded. Communication that doesn't lose information, if you're willing to lose information, then of course decoding is not going to work, it has to be approximate. But to preserve all the information, to know exactly what symbol has been sent, the minimum number of bits that you have to send is the entropy per symbol. Therefore, that's optimal.
How do you encode something with a fractional number of bits?
Right, so that's what I'm going to do next. That's assuming we get a code that has these bits. Is there a code that has that many bits for a symbol? I mean, his question is, that's all theoretical. If you could get a code that has 2 bits, 2 bits, 3, 3, 3, 4, 4, 4, 4, I believe you, but can you? There's a procedure here. Who does that? So here's how that procedure goes to generate such a code. Huffman optimal code. That's the BPC is the entropy. So this procedure guarantees that I get such a code. Yes?
No, I was asking like, let's say that you want to encode dice rolls, and so each dice roll has 2.58 bits of entropy. So how do you encode that?
I'm going to get to that after I describe this. So let me see how this works. Here's how it works. Huffman starts like a root. It's like a tree. And says, I'm going to split into, this is probability 1. That's the whole thing. And when I split in half, I get probability 1/2 and probability 1/2, right? I split in half. And then if I split this guy in half again, how much are the probabilities on each side? Probability here, probability here. How much are they? I split this half in 2 again. 1/4, 1/4. Now every time you see something that matches the probability, you can just assign that letter right there. So do I have something with probability 1/4?
A.
Okay, so I just put an A here. Do I have something with probability 1/4? I do. Right? Now I split this again. What are the splits here? Probability is 1/4 and 1/4 again. Right? Do I have more items with probability 1/4? Can I assign C or D in here? Why not? C and D have how much probability?
1/8.
So I need to keep splitting, right? So I'm going to keep splitting. I'm going to say, okay, split again. And if I split this 1/4, what do I get? I get 1/8 and 1/8. And I split this one again, and I get 1/8, 1/8, right? Do I have something with 1/8? What? C. Do I have something with 1/8? D. Do I have more things with 1/8? So what do? Keep splitting. What are the probabilities now if I split the 1/8? 1/16, 1/16, 1/16, 1/16. Do I have stuff with 1/16? That's exactly all the others, right? E, F, G. So that's a very simple greedy procedure. You're going to study greedy algorithms. Greedy split till probability of a symbol matches probability of a split. That's how come this procedure goes. Split, split, split. When you have a probability that matches your symbol, put that symbol there, stop. And you keep going until you realize it. Okay? So that's how do I generate the code from here? I say left equals 0 and right equal 1. So this is left, right? 0, 0. This is what? It's right or left? Right. That's a 1. This is right. So 1. This here, this branch which I couldn't draw properly is what? 0. This is what?
0. 1. 0, 1, 0, 1.
Now I have my codes. How do I read A? What is A from the root?
0.
What is B?
0, 1.
What is C from the root? What is D? How about E? E from the root.
1, 1, 0, 0.
1.
1, 0, 1.
Yeah. 1, 1.
1, 0. 1, 1.
Did it work? Do I get the number of bits that I wanted to get for each symbol? 2, 2, 3, 3, 4, 4, 4, 4. That's magic with this Hofmann procedure. This guy was very smart. He knew what he wanted, and he found a simple procedure to do exactly that. Yes?
If you had less characters, say you went to G, would you just...
That's what he asked. What if those things are not powers of 2? That's what you're asking. Because I pick 8, and the probabilities are all powers of 2, right? 1, 4, 4, 1, 8. What if it's not? Then it works approximatively by doing the Hofmann procedure. So that's the answer to you, Daniel. By doing this, you get an approximation. It's not exactly the entropy because it's not realizable. You can't do exactly log. If the probability is 1/6, log of 1/6, 1 over 1/6 is log of 6, gives you 2.7 bits. You can't use 2.7 bits for something because you have to use an integer number of bits. But if this is a very large, say, suppose I have thousands of items and they have a lot of probabilities there. Even if they're not powers of 2, for large encoding, this will approximate the entropy. This will approximate the optimal code. So Hofmann procedure is the one you should use all the time, whether they are powers of 2 or not. It gives you the best approximation you can. Sometimes you can match the entropy because that's not possible with a fixed number of bits per character. You can only match it exact when all the probabilities are 1 over a power of 2.
So how would it work in that situation if you just were missing the H? Would it just stop at 1, 1, 0?
It will be a little bit bigger than the H for a die because H is not realizable. H is a theory bound. It's only realizable if the probabilities are 1 over powers of 2.
Yeah.
So you can still do a bunch of bits per die, and you may get, I don't know if for a die you get for a die that has high values 1 and 6, extremely high values, and almost nothing in between. You'll get a benefit of encoding it this way rather than encoding with 3 bits per. In a die, you get 3 bits per phase, right? Because you need 6 possibilities. But if you do this, you get better for non-uniform die.
So like in this situation, if you were missing let's say the last character, would it just go up to 1, 1, 1, 0, or would it be different values?
No, this is 1, 1, 1, 0.
Yeah, so if you didn't have the next character, would
Yeah.
you just stop there?
Yeah. Which is the best approximation you can.
Yeah, thank you.
Just simplify it even farther, why can't we, like, for example, make just like A a single 0 and B a single 1?
That's not optimal anymore. A is not that frequent. If you make A, if you use one symbol, oh, okay, so here's what he's asking is, can I just have A equals 0? It would be that even faster. There is a property that codes need to be decodable. What happens if A is 0 and I send a bunch of characters? Can I decode this? Where's the problem?
I'd be confused with 0, 1, 0.
I'm going to be confused between that 0 and a 0, 1. I read a 0, I don't know if I should stop and get an A, or I can keep going and get a 0, 1. Which one is it, right? If you see a stream of characters, 0, 0, 1, 0, 1, 0, 1, 1, 1. When you read this 0, you're like, okay, is that an A or is it a B? A, 0, 1, right? So there is a property I didn't talk about that's absolutely necessary for decoding this kind of codes. Let me write it down. That's what you're going to study if you take information theory. For variable length codes, there is a condition. It's called prefix condition. A code is not allowed to be a prefix of another code. We need this condition to be able to decode it. So that's condition for decoding. Obviously in communication, whatever I send has to be decoded on the other side, whether it's a cell phone or email or Skype or FaceTime. So the problem with having a 0 and 0, 1 is that 0 is a prefix of 0, 1. And then I wouldn't know how to decode it. Is this code has that property that no codes is a prefix of another code? In other words, if you see 1, 0, 0, that says anything further cannot start with 1, 0, 0. Who ensures that property? Why this happens for this code? Why no code can be a prefix of another code? Where is that magic coming from?
Binary tree has unique paths.
In a binary tree, the leaf cannot be a prefix of another leaf, right? All the prefixes of these leaves are here or here or here, which are not codes. All the prefixes of this E are this node, or this node, but those are not encodable. How many people see that? A leaf, all the prefixes are not other leaves. Any two leaves cannot be a prefix of each other because that would mean F is on the path to the root, which is not. So the binary tree property ensures this condition. Do I need such a condition for the fixed code? Fixed length code? I mean, it's going to happen for sure because in a fixed length, there's no notion of prefix. Nobody is the prefix of somebody else because everybody has exactly 3 bits. So prefix, every code has exactly 3 bits. There's no prefix of another code. But in there, I don't need any condition. How can I decode a fixed code length? On the other side, I'm sending the code. What's the obvious procedure to decode it?
Just go 3 bits at a time.
Chop it into 3 bits, right? In here, it's not that easy to chop things, right? Because how are you going to know to chop after 0, 1? You're only going to know that if you get the prefix condition. If you know that no other code starts with 0, 1, you can chop it off. As soon as you see 0, 1, you're like, that's guaranteed a B. As soon as you see 1, 0, 1, that's guaranteed a D. Because there's nothing other code that starts with 1, 0, 1. We went way too far into coding theory here. All right? But definitely more than enough for you to do the homework and the recitation entropy problem. So the entropy is the optimal rate at encoding things if you know their probabilities. And what we didn't do, and we're supposed to do, is to talk about conditional probabilities. So let's start that. We were supposed to do an hour of that. And yeah, you guys want to stay for another hour here? Maybe not.
Maybe.
Okay, I forgot these two. Can you pass it around? There's two, I keep forgetting this, so there's 2 dates on it. I'm not worried about because I see most people come to class anyway. But I'm going to go back to the first example in probabilities. We had this 1, 2, Remember, that's for like, this die roll example, space is 1, 2, 3, 4, 5, 6. Probability of each value in here is 1/6. Uniform. But we defined two events. That last time, we're going to say event X corresponds to even. And that is, of course, the set 2, 4, 6. Here it is. That is X. So that's a random variable. Event or random variable means the same thing. When you pick something at random, what are the possible values of this random variable? That says even. It says even. So what are the possibilities when you pick something? Right, you can pick any one of those, but in terms of being even, how many possibilities are there? 2 possibilities. So this random variable is either true or 1 or false, 0. It's a binary random variable. When you pick something, you get either even or not even. Here's another event, y, which is at least 3, and this is 3, 4, 5, 6. So this is y as a set. This is a set representation. That's also true or false, right? What is the probability of true for y? If I pick something at random, what's the chance of getting it true? Huh? 4/6. And probability of getting something false? How about for event X? 3 over, right? And this is 3/6. So, how about I think of a new random variable? We've done that already a week ago. New random variable. It's called joint. It's a pair of X and Y. It's the pair. So what are the options for the pair? That's not anymore two options. They're like 4 options, right? Here's the joint table. Joint table. I can have X, and I can have Y, and I can have also not X and not Y. These are binary random variables, so each one of them is either true or false. But that's not always the case. If the random variable is age, I have so many values. If the random variable is the color of the car, there's like 20 possible colors. This is a simple example where there's only 2 possibilities for X and 2 possibilities for Y. Not all random variables are Boolean. Most of them are not. So what's the chance when I pick something to get X and Y? How many of these options are both X true and Y true? Where is this? What is this in here? There's the intersection. That is X and Y as a set, which is the same as X and Y in terms of events. When both of them happen, right? So this is both happen. What's the count for that? What's the chance of both happening if I pick an object at random? 2/6, right? How about Y happens, but not X? Which items are those? That's 2/6. How about this? X happens, but not Y. Which item is that?
2.
So that's 1/6. And how about none of them happen? 1, which is 1/6. Those are the joint probabilities. If you want to write this table nicely in a probabilities format, you say, what's the probability that X and Y pair is true? Right? True. That's 2/6. That is value here. What is the probability that the pair x and y is the pair true, false? True, false, true for x, false for y, it's 1/6. This random variable, how many possibilities have, how many possible values this my new random variable x and y has? How many? 4. Right? X is binary, y is binary, but this table is 4 possibilities. But it's just a random variable with 4 possibilities. That's what it is. And they sum to 1, right? Of course. They have to sum to 1. 2, 6, 2, 6, 1, 6, 1, 6, they sum to 1. So, what do I have in this table is, what I want to do is probability of x given y. What is to say that what I mean here is the probability of x having some value given that y has a given value. If I tell you the probability of y, the value of y, what's now the probability of x? So, how do I think of that? That is the probability of x and y. That's the same as saying probability in terms of sets is x intersect y divided by the probability of y. It's saying x is this 2, 4, 6. But now I'm not going to look at x as 2, 4, 6. I'm only going to look inside a given value of y. So for y equal true, probability of x having some value, any value, when y is true, because remember this is a given value, is now the probability of x having that value in what set? When is y true? If I tell you y is true, I restricted the set is not 1, 2, 3, 4, 5, 6 anymore. What is now the restricted set because y is true? If y is true, what's my set? 3, 4, 5, 6. Same thing, if y is false, probability of x having a value is the probability of x having that value in what set? 1 and 2. Because I already know y is false, so this cannot happen. It's got to be in here. Right? Now, what's the probability only within set for x to be true or false? It's half and half, right? How about in y? It's half and half. How about the other way? If I say x must be true, what set am I looking at? So the other way, probability of y having some value given x equal true means probability of y having that value in what set? When x is true means what set am I looking at? 2, 4, 6. So what is the probability of y in 2, 4, 6? Only if you look at 2, 4, 6, when is y true and when is y not true? It's 2/3 versus 1/3 now, right? So what we can do is to compute those marginals. Summing up this is 4 by 6, so this is sum. And summing up this is 2 by 6. This is actually y versus not y overall. Because this is all the cases with y, this is all the cases with not y. That's what we know, it's 4 out of 6 and 2 out of 6. And if we do it the other way, the sums for x, this is 3 out of 6, 3 out of 6. This is actual probability of x because it's all cases with x versus all cases without x. So 3, 6, and 3, 6 reflects the probability of x, 3, 6, and 3, 6. Those are called marginal distributions. Now, what we have here is, since probability of x and y, on one way, it's probability of x given y times the probability of y. That's what we said here. If you move this P of y, on the other hand, you get P of x given y times P of y, that's the probability of x and y. How many people follow me here? But the same thing I could say, this is the probability of y given x times the probability of x. I could apply the same reasoning to say, you know, forget about math. You can think, if I want two things to happen, what do I need? I want to get a score A in this class and marry a beautiful girl, okay? I need an A in this class first.
And you need to be handsome.
And then, hold on. I get an A in this class, and then how do I read this? What's the probability of marrying a beautiful girl given an A in this class? My chances go up if I get an A in the math class. I don't know. Right? But hold on. How can I think backwards? I say, no. To get those two things done, you need to first marry a beautiful girl, and then, what is this y given x? Get an A in the class, given the fact that you married a beautiful girl. Okay? So you can think of something happen, two things happening, as either one happens first and the other one is conditional, given that the first thing happened, or the other one happened. What's the chance of buying a car and selling my house? I could buy a car and then sell the house given that I bought a car, or sell the house and buy a car given that I sold the house. My point in here is that those two things are equal. So then I could say probability of y given x is the probability of x given y times P of y divided by P of x, which has a name. You guys know this name? Bayes theorem. I wish you had another 45 minutes to deal with conditionals. This is a conditional probability. You should write this down. Conditional and joint. Joint is x and y. Conditional is x given y. That's the Bayes theorem. And next time we'll do more examples of this. I can take a look at some meters. If we can do stuff within 15 minutes, I'm happy to take a look at some meters. You can check that very easily. You need a convexity theorem. Against the convexity argument. That's why that's the average. Here, if I take the average first, actually the average is here. The complex function. That's a complex function. It's EI. And then the maximum is the average.
After standard deviation,
Notes means what? The video?
Yeah, like the example.
So we post the book notes. The book notes have some examples. Let me just deal with this first.
Nothing under there.
So these notes here have things like, this is the tree, that's the entropy part. And then here's what the notes look like.
Okay, are these the ones that are online?
They're gonna be today.
Okay,
Like
perfect.
in an
Yeah,
hour.
that's
Right. And then I can also point to some other notes, but not the book notes. I don't know if the book does it. Does the
I
book
don't.
has
It didn't.
the book does conditional probabilities?
I think it had like just a little bit, but I know it didn't have it.
I think this is the basic of just conditionals and the Bayes theorem. There is more to it, like what I showed you last time about the expectation formula, how to prove it. You prove it with this, but you don't need that for the online. You only need these. And you know what I'm going to post? Another example of that.
Yeah, I think that normally is the
Here it is. another example with two random variables. These are the joint properties and then the conditionals.
Okay, yeah, that would be perfect.
So
Thank
within
you.
an hour or so. Okay, midterms. Can we shut down the camera? Just press the red button on the right side. Right side, press the red button. Great.